In this video, we want to talk about the solution for an infinite fin. Okay, so this is almost the simplest base case to look at. It's a good starting point to understand other boundary conditions for fins. So in the previous videos, first we talked about the differential equation and the solution for a fin of uniform cross-sectional area. Okay, so we've got this fin and it's got a uniform. This would be like a square coming down as an example. It's a sum of exponentials or hyperbolic sines and cosines. Pick whatever you want. This is the solution. We then talked about the different boundary conditions you can have. We need one at the base and one at the tip of the fin. And so we're going to talk about the infinite fin solution here. Okay. So the infinite fin is an interesting one. It's a mathematical anomaly because they're not realistic, but they can be solved. So, and we'll talk about when it's appropriate to use this. So here is convection down the length of the fin. You have minus is Newton's law of cooling, H times surface area, delta T, or you can write it in terms of theta. We don't know the length. Okay, so Z goes from 0 to infinity. Kind of interesting because then you're saying L equals infinity. You can ignore that for the infinite fin because you'll see why. But yeah, let's just assume that we have to normalize by an infinite length scale. But no worries. Let's plug it in and see how the math works out. Here's our differential equation and the solution. So the boundary condition is that theta at 0 equals 1. So the temperature at the base equals TB. T equals TB at 0. Or T equals T infinity, okay, meaning theta equals 0. If you look at what our definition of theta is, our dimensionless temperature, as Z goes to infinity. Meaning if the fin is long enough, you've got heat loss down the fin. So if it's infinitely long, you will have enough surface area to fully lower the heat to the temperature of the cooling fluid, which is T infinity. So if it's long enough, we assume it'll get to T infinity. So let's see how to plug this in. The second boundary condition is going to be an easier one to start with. And the other important thing to note is the exponential functions, as opposed to the hyperbolic sine and cosine functions, are also going to be easier to plug in, although technically it doesn't matter. So let's say theta as Z goes to infinity equals 0. So let's take this function, plug in Z goes to infinity. To do that, you have to do a limit. So you're saying 0 is the limit as Z goes to infinity of C1e to the mz plus C2e to the minus mz, okay? And if you look at these two functions, e to the minus x converges at z goes to infinity, it goes to 0, or x is whatever the argument goes to infinity, it goes to 0, whereas e to the x diverges infinitely, okay? So there's no way this will go to 0 if this term is in there. So that's nice because that means that this boundary condition is only valid for C1 equals 0, okay? Like that, this function can't be there for it to actually be 0 at this boundary condition. Okay, so we're left with theta of Z equals C2 e to minus mz, okay? So now let's take this expression and we need to solve for C2, and we'll do that by plugging in the first boundary condition, which is that theta at x or z equals 0 is the base temperature, or theta equals 1, okay? And so if we plug that in, it's 1 equals C2e to the 0, okay? E to the 0 is 1, so that just means 1 equals C2. And we're left with this function, theta of z equals e to the minus mz. Okay, this is why we like infinite fins. This is a really easy expression. The temperature profile has an exponential decay. That's pretty straightforward. How do we compute m for an infinite fin? Okay, so keep in mind that this m was a collection of parameters that had L squared, the length of the fin, the thermal conductivity, whatnot. Anyway, the length of the fin is an issue if you're assuming it's infinitely long. So this is kind of the rare example where non-dimensionalizing this expression has kind of made it more complicated. It's not a big deal though, because if you plug it in, okay, so theta of x, let's get rid of the z dimensionalization, is going to be e to the minus mz x over L. Okay, so I'm plugging in x over L for Z. You can do the same thing. Now plug in your value for M. So theta of x equals e to the minus, and M is going to be now HP over KAC time to the 1/2 times x. And what happens is this L is going to cancel out with this L when you plug in M. And so in the actual expression for theta, it doesn't depend on length. The infinite fin does not depend on length. It just kind of looks like it when you put it in terms of M and Z, okay? But once you plug the actual values in, it doesn't depend on the length scale. So everything's fine for an infinite fin. Let's just write this. L cancels out, okay? And we want it to be dimensionless because if it wasn't an infinite fin, then non-dimensionalization is certainly the way we want to go. It's just tricky to non-dimensionalize something that has an infinite dimension. Okay, so we've got our solution. We're basically saying if we look at this would be the length of the fin. Let's compare what the temperature starts at. Theta equals 1, and then it's going to decay exponentially down the length of the fin. And here we're assuming this Z goes to infinity. So it's always going to decay down to 0 because the limit as an exponential goes to infinity is always 0. So the limit of this, we'll say the limit as Z goes to infinity equals 0. I mean, that's just the limit of an exponential. Okay, so all of these will decay to 0. And what happens is if you increase M, meaning you increase convection on the surface area, you increase the perimeter, meaning you increase the surface area, or you decrease the thermal conductivity, then you're going to get the temperature profile will decay quicker. Okay, you'll get a sharper drop in the decay. So yeah, you get this exponential decay. Let's write this in real units so you can kind of see what this would look like. So, you know, dimensionless units are real as well. I mean, no unit is real or unreal, but more common units, I'll say. So the definition of theta is T minus T infinity over T base minus T infinity equals e to the minus HP over KAC to the 1/2 times x, or T of x. Let's rearrange this, solve for T of x. So we need to multiply this over and then add T infinity. T of x equals T base minus T infinity times e to the minus HP over KAC to the 1/2 x plus T infinity. So this is why we non-dimensionalize it. You don't want to write this expression. I mean, this is much easier than this, okay? But this one's kind of more intuitive in terms of realistic numbers. So this is our expression, and you can clearly see it's exponential. So we're talking about increasing M. We're talking about increasing, you know, this term for an infinite fin. So yeah, exponential profile. We have the temperature profile. Once we have the temperature profile, what's the other important piece of information we want to know for heat transfer? That's the heat transfer rate, okay? So how quickly is heat being lost from this fin? So the heat transfer rate, you know, Q. We've told ourselves that Q equals Q everywhere, okay? So there's no generation going on. There's no heat accumulation anywhere because it's steady state. So energy in equals energy out everywhere. So it doesn't matter where you evaluate Q. You're going to be talking about the same thing. For fin, though, you need to be very careful where you evaluate Q. Because for Z greater than 0, meaning somewhere down the length of the fin, you have convection and conduction, okay? Whereas at Z equals 0, you only have conduction, okay? So look at Z equals 0. You just have conduction right at the base. There's been no exposed surface area. All the heat going through here, if that's Q, then the problem is at this position, that's equal to all of the heat going through here still, plus all of the heat lost up to that point by convection on the surface area. So you don't want to have to account for the fact, I mean, let's write it out. Okay, we're going to say that Q, if we did this for some place Z greater than 0, it would be minus KAC dt dx at x equals some position x1. So this would be at an example at x1. So it'd be all the heat passing through due to conduction plus all of the heat that's been lost due to convection. Okay, so it'd really be minus the integral from 0 to x1 of HAS t infinity minus t dx. So this is minus HA delta t, or HA t surface minus t infinity. Where here t surface varies down the surface. So the problem is this is tricky. You don't want to do this. So you can get around this by just saying we're going to compute Q right before any convection happened, and then you're always talking about all of the heat going into the fin. So you could also just say equals minus KAC dt dx at x equals 0. Okay, so this is at 0, and this one would be at x1. So it doesn't matter. You can always do an energy balance to account for the heat anywhere, but it does matter in terms of how easy the math is. So if we take this heat transfer rate and we look at it at the base of the fin to make the math easier, this is our expression. So it's just conduction. And let's look at it in terms of theta, okay? So Q equals minus Ka. And then if this is theta, then again, we've done this a few times. We need to get dt. So we'll multiply this over, take the derivative of both sides. You'll get Tb minus T infinity of d theta divided by, and it's the same thing on bottom. dx, we'll bring this up and take the derivative. It's going to be L dx. Okay? And this is going to be at z equals 0. And so let's take this derivative of theta. We know theta. We just solved it. Theta is e to the minus mz. So if you take the derivative of this, it's going to be a minus m out front. So the minus m is going to cancel out. So you get q. The negative cancels out. We have m ka tb minus t infinity of e minus mz divided by L at z equals 0. And again, if we plug z equals 0 here, this would be 0. So this e to the 0 is going to be 1. So you're left with q equals m ka tb minus t infinity over L. And let's plug in m. So what did we say m was? M is going to be L squared HP over 8 KAC. And so we're going to have L and then HP KAC to the 1/2 multiplied by K. These are all cross-sectional areas, by the way. KAC. And then this is going to be TB minus T infinity. And if you look here, KAC divided by KAC to the 1/2 is going to make this KAC to the 1/2. And so you're going to be left with Q equals HP KAC to the 1/2 T base minus T infinity. And this is very familiar looking equation. So I can rewrite it in this way. Let's write Q is equal to some HA fin. Let's just say this is HA for a fin times TB minus T infinity, where HA fin equals HPKAC to the 1/2. Why am I doing this? Because this looks exactly, I'll say it looks like Newton's law of cooling, okay? Newton's law of cooling. HA delta T. HA T surface minus T infinity, or minus HA delta T. That's Newton's law of cooling. Q equals HA T surface minus T infinity, or depending on the, this is in the positive X direction. So fins are no different. The heat loss down a fin is just HA delta T. But your HA is a little different. You can't just write H times the area of the fin. It's actually HPKAC. This collection of terms accounts for H times the effective area of a fin. And so let's see why this happens. And the idea is you can think of a fin as Newton's law of cooling, however, with an effective HA fin instead of HA that you'd have for Newton's law of cooling. And this HA fin is for an infinite fin. And this HA effective accounts for the fact that the entire fin is not at TB. Okay, so look at Newton's law of cooling. T surface minus T infinity. But if you look at a fin, here's TB, the temperature at the base of the fin, and then your T varies down the length of the fin. So you've got this complicated temperature profile for the surface temperature. So Newton's law of cooling occurs over a gradient in temperature down the length of the fin. But if we just write it as if it was all at the base temperature of the fin, then we can write an effective HA to compensate for the fact that everything is not at the base temperature of the fin. Okay, so this accounts for that fact. So to visualize this, if you had no fin, then the surface would cool by HA T infinity minus T, negative HA T infinity minus T surface. Newton's law of cooling. Now you have a fin, it cools by the same thing, but you need to know the temperature profile for the surface temperature. So another way to write this exact same problem is just to pretend that there's no fin. So then this entire surface would be at TB, and you would use an HA effective, which accounts for the fin. Does that kind of make sense? You're basically representing, instead of a temperature profile, an effective temperature and an effective HA to account for the complex temperature profile down the fin. So that's kind of the gist of an infinite fin, and how we compute the temperature profile, how we compute the heat transfer rate. So the takeaways are that, we have this differential equation, we solve it, and then we plug in the infinite fin boundary conditions to get our variable, our constants in this differential equation, or this general solution. So it's an exponential temperature profile down the length of the fin. So the temperature never changes at the tip because it's infinitely long. And the heat transfer rate looks just like Newton's law of cooling, but we've got an effective HA term to account for the fact that the entire fin isn't at the base temperature. So it's an effective Newton's law of cooling if you just put in TB as your temperature difference. So that is the solution for an infinite fin.